Thank you very much. As Jordi explained, I'm in IBM R&D. I'm the community engineer lead. That means that, well, we are in charge of the education platform, and also the KIDE development, and also the web, the documentation, the tutorials, and all the documentation related and education related to the quantum side. I'm also involved in the HPC side of the quantum development into R&D, so that means, and we will explain during the presentation, that one of the key points for this year in the IBM view is to meet HPC and to see how quantum can help HPC and mostly how HPC can help quantum. Okay, so well, this is a little of my background. Quantum, as you know, we have a very deep background here. The audience, I know some of you in HPC. We have several problems that we cannot solve. We are a small planet, but with big problems to solve. Nothing that you don't know. These are some of the challenges we have. So the presentation is which are the challenges we have as humanity, how quantum can help. Then I will explain more or less the state of the art and what is going to come in the next years. So these are the challenges we are facing, or some of the challenges we are facing, where we cannot arrive. For example, improving iteration fixation. That means that if we want to simulate some molecules, we are not able right now in HPC, even on the particles simulation applications we have. We are hoping that quantum can help in some of these problems. So the mission of IBM is bring useful quantum computing. What does it mean? Well, start changing. And this is not just IBM. I would say it's the market itself. So let's try to take the presentation not as an IBM, but as a market trend. Okay, useful computing quantum to the world to make the world quantum safe. What does it mean? There's been a trend during these last years where the people is asking for quantum advantage. Quantum advantage is a very difficult concept because usually it's linked with to our classical devices, but the classical devices are advancing every year, so you cannot set a quantum advantage at some point. What concept we are bringing with the quantum community is the useful quantum, where quantum can be useful and give us some advantage over the HPC or over the classical computing. And this is what we are looking for. So what are we looking at? It's systems. This is the summit, but you have also the frontier from HP. It's 1.5 exaflops, Mare Nostrum, a lot of them. We are doing a lot of simulations, a lot of problems, but we see that HPC is not capable enough. For example, you want to simulate the airflow through an airplane, it's not possible right now. It's easy, but it's not possible. We cannot even simulate some small molecules. We have to do assumptions, and we have to work on those assumptions. For the airflow of the airplane, for example, we do a wing, another wing, we do the main, and then we join everything together. So yeah, there are a lot of problems that still in track tables. And this is a, do I have a pointer here? Yeah. This is a slide that is evolving during the years. At the very beginning, we haven't had this part. That is part of the problems that we cannot address with the classic, and we hope we will address with the quantum. But in the meanwhile, we are discovering new capabilities for quantum. We are also discovering that we need help. So, for example, what we were talking about, the HPC can help quantum, for example, for transpiling some of the circuits. And for that, you need to put all the circuit in the HPC cluster. And it's quite demanding in memory and also in, well, in computation, not too much, but in memory is quite demanding. So that means that we are increasing problems that we can address today because of the problems we cannot address. So at the end, It's a mix, and in fact, there is a part of the quantum just dedicated to evaluate the type of problems we have. Example, the caffeine. Right now, we cannot simulate the caffeine in an HPC. It's 10 to the power of 48. It's impossible. It's impossible to simulate in an HPC. And this is the kind of problems we are hoping quantum will solve in the near future. We could represent, the caffeine with 160 logical qubits. This is more than the atoms that we have in the Earth. So obviously, we cannot represent that kind of memory into an HPC cluster. So what is the state of the art of quantum right now? There are plenty of providers that can give you quantum. I won't talk about them because I don't want to mess any message, and I don't want to talk on their behalf. But I can explain what is in IBM. So in IBM, we have 460,000 registered users, but the most important is the systems we have available. From 2016, we provide quantum access for free for anyone that wants to join the network. You can just go to ibmquantum.com or search in Google IBM Quantum. I'm going to get luck. And the first link, you can go there, you can register, get your own token, and send code to the quantum devices, real quantum devices. These are all the ones we have. For free are from 27 and below. Some of the, 16 and below, sorry, 27 is for the cloud access, and the other ones are for premium access. This is going to change this year. I can explain why, but probably we will have more premium access for the open plan, so people can probably will work on higher devices. And this is something that not only IBM, but I think the providers are very willing to do. It's to provide the access for the community so the scientists can grow and can grow also our developments. When you join our web, you can see everything, the error rates, you can see the frequency, you can see the topology, the type of gates we have in that processor, and also the error. So with that, you can do papers, you can do research, you can do whatever is worth it for you. Quantum Innovation Centers. This is the data centers we are deploying around the world. So when people ask, is quantum real? Yes, it's real. These are data centers deployed around the world with on-premise systems. It's not cloud access to our systems and managed by ourselves. This is on-premise systems. The first, our data center in New York. The second one is Fraunhofer. It is in Germany. Even if it is in our facilities, the server is owned by Fraunhofer itself, and all the other ones are in their own facilities. And we are planning to deliver at least a couple more in 2024, and one of them is going to be here in Spain, in the Basque Country, with the Basque initiative, Nicker Basque. They announced like 3 or 4 weeks ago in April. So with that, I can say that Spain is one of the top investors in the world. I would say it's in the top 10 for sure. And if I have to talk about IBM team, I would say that a lot of our researchers and developers are in Spain. I would say it's the second biggest group in the world. So yeah, Spain is investing, is a good player. And this is how it works when we have a common developer with the people in our network. Open plan, premium plan. Usually, we publish an algorithm. We start with some paper. People take that paper and improve that, apply to a user case, improve the method, use variational methodologies to improve with classical computation, whatever. Then final customer applies a use case. Nowadays, usually it's in a theoretical way. We can simulate some of the things, but for example, an optimization portfolio for banking could use 1 million, between 1 million and 6 million qubits. So it's only on theoretical. We can do tests of less quantity of qubits, but mostly on theoretical. So it's papers, but it's preparing ourselves for when we have that quantity of qubits. And this is one of the questions probably when we will have. I will respond that on the roadmap view. So when customers approach to us, which are the use cases they prefer to talk about? Well, the ones where quantum already it's giving some advantage, even if it's on the theoretical side. Mostly it's simulating quantum systems that Feynman said in the past. If you want to calculate the nature, you have to do it with quantum systems because it's the only system that can really simulate the nature. In this case, everything related with chemical materials discovering, it's a good use case. Also, artificial intelligence and optimization on Monte Carlo. At the end, it's a way of managing a lot of states that the classical computing cannot manage, or conditional probabilities. Quantum is very good in conditional probabilities, and the interaction between qubits is also very good for those problems, to attack those problems. Okay. This is what we are working with the customers, and again, if someone is asking himself or herself, is quantum a reality nowadays? Yeah, we are doing these kind of things with our customers. And 3 examples. For example, it's developing of different batteries for the electrical cars with Daimler. Logistic optimization with Exxon. We also did some materials discovery here with Exxon, and also financial improvements in terms of fraud, also risk analysis, again, on optimization portfolio. What is JP Morgan doing? Honestly, no. At the end, it's okay. What are the customers doing? What they are doing is try to simulate a financial case with less qubits than they would need, create the theoretical problem, solve something that will be doable in the classical nowadays, but see which is the advantage. And looking at the advantage, sometimes with short is a quadratic advantage, sometimes it's a linear and half, but that gives them the inflection point where they will find the quantum advantage, depending on the number of qubits. So they use that, they keep the paper hidden for the day they can use that. And that day, they will have an advantage, maybe in 2, 3, 4, 5, 6 months, but 6 months of advantage in a multi-billionaire business is a lot of money. So that's why they are investing right now. So bringing the quantum computing, the useful quantum computing to the wall at the end is a way to find the better system and when a good system is going to be better than the classicals. To evaluate a good systems, we have created, defined some metrics. For me, these metrics are very important, and I'm going to focus only on the performance, but explain briefly the frictionless and the capabilities. This is the value of the quantum computing that we see. Performance, I will go deeper. There are 3 metrics in performance. So if anyone explain you any quantum, I would say with these 3 metrics and see if it's a good one or not, more or less. And there is an analogy with the classical. I'll try to explain. Frictionless, for me, it's how easy is the new environment to get into. So if I'm at how much I have to learn to get into the quantum. We are trying to do totally frictionless. We are working on Python, we are giving libraries. At the end, you need some knowledge. You need to know that you can work on phases. If you move the phase, you are doing some amplitude variations, and you need to understand a little of the quantum. But to not have resistance in terms of Python libraries, primitives, that is preset programs that we will provide and you can use easily. This is one of the main points we are thinking. We have had several errors as IBM in the past. For example, the cell processor, probably most of you know the cell processor. It was a very good processor with the Synergy processors and the principal one, but the software stack was, I wouldn't say horrible because I was working on that software stack, but it was not the best one. So for us, this is very important, that the people can start working very, very quick. Capabilities, for example, right now we have dynamic circuits in OpenQSM3, and we have several of our systems already compatible with that technology. To your systems, the most capabilities. This is functional improvements that our systems or the quantum systems can provide. But let's go to the processors. What is performance? Performance is scale, quality, and speed. Scale is the number of qubits. Obviously, every year there are new hardware with more qubits, more operations, more states you can handle. That's simple. And this year we have announced Osprey. Here you will see that the most important is Aaron. I will show you. Quality. We can have a lot of qubits, but if the error is unmanageable, you cannot work with. So for that, there is a metric that we define it, but seems that the industry has adopted it. So there are providers that has this quantum volume metrics to the quality of their systems as well. And well, the analogy of the number of qubits, I would say, is the analogy of the number of bits. I think there is plenty of people here that when we were younger, we're still young, working on the video games, for example, passing from 8 bits to 16 bits to 32 bits was always an improvement, a real improvement. So with qubits, we are in the same. With this, we are in the quality. I would say that it has an analogy with more laws because we are doubling the quality every year. It's not the number of transistors that we have in the chip, so it's not a real simile, but yeah, that would be and it became real every year. So this is, I don't know if it's going to the quantum volume, but until now it's been real, the prediction. And speed. Speed is very important. It is something that we were focusing last year, and it's very important for this year. Is the CLOPS, is the circuit largest operations per second we can do. That means the parallelization you can do within the qubits and also the deep of the circuit that you can go. And this is very important at the end. If you cannot do it quick, it's, I wouldn't say useless, but less practical than a quick one. Okay, these are the 3 metrics. Quantity of qubits, those qubits, and how fast you can calculate those qubits. And now is the roadmap. The roadmap that we have been accomplishing every year. We have Osprey right now. We announced that in the Think. Taking account that when we announce something in the Think, I'm sorry, in the Think in the Summit, usually we have a big announcement in November. That means that, for example, Osprey, we have the hardware. Then we need to progress for access that hardware through the cloud and the systems, and that takes some time. Osprey is now online. Internally it's online for IBM, and probably in the next weeks will be also available for everyone. For this year, what we are announcing is Condor. vertical growth, 1,121 qubits. But the most important announcement is going to be Heron. We are super excited with Heron. Heron is chip interconnection. That means that from now on, we can interconnect different QPUs. And that means it's going to be an explosion in the next years. But we have to link that with the roadmap for 2024, which is Flamingo and Crossville. Flamingo is going to use vertical growth with interconnection. And Crossville is going to use intraconnection between QPUs. That means that we are going to have chipsets bigger with different QPUs interconnected, and those modules also interconnected with another one. Arriving to Kookaburra, well, the names are, we are freaks, okay? So the most important, the vice president, it's from Australia, is Jay Gambetta, probably some of you know him. And all these names are Australian birds. As well as the machines has city names. We start with Coruña, Vigo, because the first developers were from Spain. And now every machine has a name of a city. Manhattan is the Osprey one. Well, that's it. Kookaburra is going to be the one that is going to link both technologies, intraconnection and interconnection. So we are projecting more than 40,000 qubits for 2026. Between 10,000 and 100K, but at the end, what is important of the roadmap is that there is not going to be limitations on qubits, honestly, because of the technology itself in 2026. There's going to be limitation because supply chain, because we cannot do 100 of these systems per year, because probably there is not going to be anyone that can pay billions to create a super big supercomputer with millions of qubits. And that's going to take some time. Improve the supply chain, improve the capabilities with HPC, improve the calibration, taking account that we spend maybe 3 months for calibrating a system, 3 months for freeze the whole system, so you cannot deploy a lot of systems in 1 year. This is some of the limitations we have, materials, etc. So the technology itself is not going to be really a challenge. There is going to be much more challenge to bring the real quantum computing to the society. And some of them are going to be here. And we hope some of you help us and the community to create solutions. As you can see, well, dynamic circuits is on this year. You know that dynamic circuits improve a lot. And if you, for example, this is parametric compilation that more or less, I would say it's dynamic circuits. In dynamic circuits, you don't compile and transpile every single actuation you do. You pass some parameters and then you can send an array of operations and not compile and transpile in any single operation. So you can provide much more bandwidth. 3D primitives, and I would say quantum serverless with circuit knitting and circuit libraries. What does it mean? We take the whole circuit, we optimize that circuit in better circuit with the transpilation, and then we cut the circuit in different parts and we send to different backends. We calculate that in parallel and then join the outcome. That needs a lot of memory, that needs a lot of operations with classical, but also reduce the error a lot. This is one of the techniques we are using for and after that, these are one of the techniques for sure. And after that, we will use more techniques on error suppression and mitigation. thinking on research correlations, mitigations with metal, and a lot of more techniques that we are expecting to find in our way to our final solution. We are not extending the roadmap neither because we need some breath on the hardware. It's been a super race to know what's going to be also the focus in the next years. So, for example, these were some of the advantages or some of the big thoughts we achieved during 2022. I won't go through all of them, but just to remark, dynamic circuits at the end of the year. Well, quantum safe is not really quantum, it's more classical. The serverless and the circuit, I think this is just developed last year. I mean, we are always working in MVPs. Last year, the project started July, developing on September. We were closing that on December. Quantum-centric supercomputing, this is one of the projects we started last year, but it's going to be key during this year, and at the end it's HPC-centric. We are trying to do it HPC-centric. And the 100% challenge, for example, this is a challenge. The solution probably is going to be for the next year. This year we are focused on Osprey and Heron, and we will work on this challenge also by the end of 2024. This is hard. This is 100 qubits, 100 depth. Well, some of the things that we already done this year, this is a paper, you can go and read it, where we achieve almost totally error correction with 23 qubits. We were talking about several times that the big scientifics, the more senior ones, forecasted between 1,000 and 10,000 qubits to achieve a logical qubit. Well, depending on the law, depending on the outcomes you want to achieve, you can do that with 23 qubits. Make some math. You can make some math and arrive to what we can achieve on 2026. So this is the kind of techniques we are looking at. In the meanwhile, the hardware is advancing. Okay. So I just remarked that the full processor can encode a logical qubit with distance from 3 and perform several rounds of fault tolerance syndrome, measurements that allow the correction of any single fault in the circuit with 23. Take a look to the paper. It's very, very interesting. So, what is going to come? What is going to come in the future? System 2. This is the control electronics. This is the classical side of the quantum side. Well, at the end, the quantum, the Q transmons in the supercomputing technology. The transmons, you set the transmons in the states, but at the end, what you are doing is sending microwaves that are created with ACIX, ASICs. And all this is managed by the classical computation or the classical systems attached to the quantum one. Okay, so to develop that is also very important, but in System 2 we are giving a main position to that electronic. So it's very important. So this is an example of what System 2 could be. It's cryogenic platforms in an hexagonal. So it's not that just you've seen the quantum processors with the wires, okay, arriving to freeze the QPU. Now what we are thinking or what we are doing is to freeze the whole capsule and then put the systems on a freeze capsule. This is the change of concept. So you can put, that's for Heron, and we need to interconnect and keep them at 0.50 millikelvin. So with that, we can put a lot of them. And we will connect the classical. We can have a classical CPD, but the classical connected to the quantum is going to be integrated. So it's going to be the data center of the future, as we see, it's quantum-centric with classical connection. It cannot be splitted. And this is how we see the future of the quantum data centers and mostly HPC. This is our vision for hopefully end of 2024, 2025 for HPC centers. This is pictures. We are good on time, right? More pictures just to show you some of what our designers are doing. They have to justify the job, you know. So we need some pictures, and we have also a video. So if you want to keep updated of the quantum, I really recommend this book. It's the Quantum Decade. It's the principal players, trends, technologies, and we updated this at the beginning of the year. It's really an interesting book to take a look. And this is part of all the open source SDK we have for development. You can just download it on your laptop, use Qiskit, and send the executions to real hardware. We are delivering right now the new courses. John Watros is a reference in the quantum community. He's from Canada, and he's developing deep knowledge courses. We have the textbook. This is all we have. I'm in community, and I have to give some publicity of what we are doing. This is the textbook. You can learn here from what is a qubit to do the short algorithm, or even apply VQEs or machine learning techniques to quantum systems. Explore more about quantum computation and Qiskit with the documentation in qiskit.org or IBM Quantum. You can go there and whatever you want in terms of education material. Get the Quantum Developer Certified in IBM. This is the only certification, as far as I know, in the market, and you can be certified with the knowledge. We have also a syllabus in the textbook. If you follow the syllabus, you will have the knowledge enough to pass the exam of the certification. It has a fee, the exam, but it's quite flexible on the dates. The Qiskit YouTube channel with the courses of John, and also the research and education program. Probably some of you want to create some papers together with IBM. Go there, apply, and you can work with some of our research staff and get some advices, or see if there is a project you can contribute with. So these are the links if you want to read that, and that's all from my side. Hope it's been interesting.
Thank you so much.
I guess we have 5 minutes for questions.
Yes. So questions?
Oh.
Coming there.
That's too sharp, Miguel.
No, it's just about curiosity. You know that in classical computing, HPC, we are facing some challenges, such as the energy efficiency, and that's one of the reasons why we cannot scale too much. Apart from Moore's law, and we are hitting the walls of scalability. You have been talking about a theoretical limitless scalability of quantum computing. So how do you face the energy efficiency, or what are the metrics that you are using to have a feasible, a viable quantum computer? And not only because of the price of the electricity, but because of the availability of power itself.
Yeah, right now the power is not a problem for quantum computers. So the consumption of a QPU is, I wouldn't say dismissible, but if we take in account the control side, on the quantum side, the control side is who is consuming all the power. So the quantum, we are talking about milliwatts for the whole system, and you can join all them. The capability of power of computation that it gives related to the consumption, right now is not a problem. We are not seeing problems there. Probably we see more problems on the HPC that has to be linked to that. I don't know, so.
Yeah, so would you say that quantum computing is another improvement of quantum computing over classical computing is also the energy efficiency?
Absolutely.
All right, thank you.
Absolutely, yeah. And it's very easy. For example, you shouldn't store, so if you have to calculate with classical computer, you have to store all the states in memory. And with quantum, you can calculate in the qubit. So if you don't measure, you can do all the calculations and you don't need all the registers. So that's a way of improvement, for example. But yeah, nowadays you can join a lot of quantum systems and the consumption is not a problem. It's much more efficient.
Thank you.
You're welcome.
Hello, my name is Marco. Thank you very much for this interesting pitch. I'm very interested into the interconnect, how you connect to quantum. I mean, I'm wondering, Gigabit Ethernet, InfiniBand? Please let me know.
It is not. That was my very first question as well. How are you doing that to maintain the states? Right now, as far as I understood from the research lab, it's a superconducting connection.
Hi, thank you for the talk. So you mentioned that there's some supply chain logistic issues which might impact how you can scale up in the future now that you have this bridge that you can connect different chips. Are there other resources like helium or other things involved in the refrigeration that might be limiting factors?
Not what we are aware of right now. Taking account that we cannot create a lot of systems, we spend for the full cryogenic capsule, we spend like 6 months to refrigerate that. It's a very slow process.
And it's a closed system.
Yeah, yes, and it's very slow, very slow. It's, I mean, and the last millikelvins, they are very, very slow to get down. No, we don't see right now a problem, honestly. I don't know in the future.
Thank you.
Hello, my name is Philippe Partella. Recently, we saw some article complaining about the I/O throughput, that this could be limited to the quantum computing.
Yes, the I/O is a limit because right now, well, in fact, with Osprey, it starts some limitations. It's 433 qubits. The result of that, sometimes we are talking about terabytes, and to move terabytes with classical communication, it's a problem. Yeah, this is a challenge. One of the challenges we have right now in our table to solve. Some solutions, it's high bandwidth networks like InfiniBands, increase a lot the number of registers in classical. But yeah, this is something that we are facing. And honestly, I cannot give you an answer for the future because we are solving the near term right now. And in the near term, the problem is the delay. What we are doing is trying to put in parallel different systems. So when we are waiting for the outcome, we can start introducing another calculation, and we are filling the gaps. This is more or less what we are doing now.
Thank you.
Hello, my name is Oscar. I have to. I will begin saying I know nothing about this topic. So the question could seem a little bit stupid. So I apologize for those that you already know.
No question is stupid.
Well, so I arrived late. So even that against me. But I've been hearing you talking about computers with 1,000 qubits. More than 1,000 qubits, hundreds, but anyway, more than 1,000 qubits. And at the end of your talk, you were amazed of presenting a paper that talking about a QCPU, I think you call it, that was using 23 qubits.
Yeah.
Last time I read about quantum computing, the paper I read, the thing I read was talking about, I think, 8 or 10 qubits. So could you please explain a bit this huge difference of numbers? Sometimes you were talking about a QPU that was working very well with 23 qubits, but at the same time, you were talking that we will be able to use thousands of qubits at the same time. So
yeah, sorry, probably it's misexplaining from my side. The qubit I was amazing on the paper, it's a logical qubit, which is fault tolerant. 3 qubits, physical qubits. So taking account that if you have, just for having the same distribution, 230 qubits, you could have 10 logical qubits. This is a huge, so a logical qubit which is fault tolerant. So means that you can have an infinite qubit and do infinite calculations with that qubit. This is an awesome achievement. What I mean is you have 433 or thousands, you have to divide for 23 and you will get the number, the extrapolation of number of logical qubits, which are fault tolerant. What I mean is that we have a long way right now. Like if you have the memories without the CRC, without any kind of protection, that memory is not reliable. So for that, we create more transistors, we put redundancy, we create the codes, and now you have a reliable memory, right? It's the same with the qubits. So what I was amazing because, and what it shocks me, because all the forecast, all the prediction was that you need between 1,000 and 10,000 qubits to achieve a logical qubit. So we got it with 23 this year. This is the difference. So if you go to a 40,000 qubits machine, and you were talking about 1,000 qubits for getting a logical one, you will get 4. With the 23, do the math. And that's what it's surprising me. You're welcome.
Hi, my name is Oscar as well. What a coincidence, right?
Hi,
I
Oscar.
was wondering if you are aware that any other country developing quantum CPUs as well. I mean, we just saw some allied countries, you know, Japan and Switzerland, whatever, but we didn't see any mention to, I don't know, China, for instance. Are you aware how, in which state they are in right now?
We have Albert here. Well, we have Kilimanjaro here. In Spain, we have Kilimanjaro. We have QSight. QSight is developing quantum computations. Kilimanjaro is developing QPUs. Oxford Technologies in UK is developing quantum brilliance in Germany. QLM, it's plenty. It's plenty of places in the world. Regarding China, I don't know. Well, no one knows. We know they are doing a good job, but exactly numbers, I don't know. Korea, they are doing a lot of South Korea, mostly in communications, and Japan, absolutely. And quantum technologies is not only quantum computation. IBM is focused on quantum computation, and all the companies I mentioned, except QSight, most of them also focus on quantum computation. But there are other things: quantum operation systems, quantum memories. In the Netherlands, there are some papers regarding quantum memories, very, very promising. ICFO, just 2 or 3 weeks ago, also maintained some states. It's a very starting point of the quantum technologies. I would say quantum communications, quantum computation, quantum sensoring. It's very important also. And in our way, we will learn a lot of things. Question, by the way. So we could spend hours talking about that, because I see a lot of research initiative in Europe, but they are bet for different providers. In the States, there is plenty. I would say the countries with less focus, or the continents with less focus, will be Africa and South America. But even that, they are very, very interesting. You're welcome.
For last question, we are going to have a roundtable after all the blog. Okay, so please go ahead. Thank you. So my name is Carlos, and you've presented some or one industry use case. Considering the speed that the technology is advancing, do you envision companies having their own quantum computers on-premise? Because you've presented also some on-premise deployments. Does it make sense for industry to have its own quantum computer, or do you envision IBM providing it as a service, considering the speed of the technology moving?
Difficult question, because of our customers. Our ambition would be everyone accessing to the cloud, because it's cheaper for us and cheaper for the customers, but they do not want that. So yeah, we were surprised why you want on-premise if it's only research. GDPR, it's my code. I don't want anyone looking at it. So a lot of different causes that you can imagine. Most of them related to security and IP. Most of them related. That's why most of them want on-premise. Is it worth it? I would say for a financial or for a regular customer, not related with research, right now is, if I say it's not worth it, it's like I do not want to sell. No, it's not the case. I want to sell that, but I will have that linked to a research institution. So our vision right now is, if we have some quantum computers, we should fill them up until the top, because it's limited technology. So if we link that to a research institution, we are some kind of assuring a lot of people is researching on that. So if you are a final customer and you want a use case, and this is Albert's view, no IBM, I would prefer you working with a research institution so you can fill up an extra 30%, and we can better use the quantum computers, which is quite limited in the world right now. I would say that when we achieve the millions of qubits, it's going to make sense for a final customer to have it.
Thank you so much.
Thanks to you all.